So let's do the recap. Last time, what we learned is what? So, do you remember last week we learned the representation of the conformal algebra in D greater than 2? So that's what we learned. And we considered start with the whatever operator mu1, mu L. So that is the rank L, symmetric, traceless, primary. Okay, and then you start with this guy, and then act lots of P and so on, and try to find the singular vector, whatever singular operator, say O A, and then from there you have a lot of null states and so on. So this OA is characterized. So this is a singular vector characterized by k mu acts on OA is equal to 0. So OA is inside of a module. OA is inside of a module, gamma of this O mu 1 dot mu L. But module is you just act lots of P, how to say, P momentum operator on it, and then you get the infinite family of the states. But it has some singular vector, and of course this is a no vector because OA itself is the written. So since it's OA itself is written in some whatever of psi. So there's some states in here, and if each acts on P mu to get the OA, right? Okay. Because it's a conformal family. So there is this. So it's a descendant. So there is some states that acts on the, and if you act on P, you get the singular vector. So therefore, of course, if you just have the OA, so this is some psi k mu, or P mu psi OA, and this is the, if you use the P mu is the dagger of k mu, so OA. So therefore OA itself is null. Okay, of course, and everything here is null. The same because of same argument. But you get the irreducible module. Okay, and I have to mention that I didn't mention. So in 2D, D equal to 2, T mu nu is decomposed into the two part T ZZ, and which I call it. I don't remember the details. Some number is I call it holomorphic now. I think most like a 2 pi in my notation. And 2 pi T bar ZZ bar. Yeah, I call it T bar Z bar. Okay, so like this way. And then if you compute TZ and T0, what you get is T to the 4th C over 2 plus Z squared 2 times T0 plus Z, and what you get is, so what is the numerator here? Huh? There del T, okay, and so on. So therefore, because of this one, because of presence of this one, T of Z is not the primary. And then, yeah. And then we know that if you just do the transformation from Z to whatever, W of Z, T of W is the del W del Z minus 2 T of Z, and then you have a short term derivative. That's what you learned from the homework. So the extra short-term derivative you will get, that's you already knew. However, d equal to greater than 2 t mu nu is a primary. So this one I didn't emphasize it, and then I told you that so you start with like a state operator component t mu nu. Actually, this one is for primary state, and if you act on this one, if you act on p mu, t p mu nu, so this is the singular last time. So that's what I told you. But I didn't mention this one because I forgot to mention. So it's important to mention that. So I have to explain why this is primary here. So that I have to explain why this is primary. So of course this T mu nu is the symmetric traceless in CFT and rank 2 tensor. So therefore it's one of the. So T mu nu belong to this guy. So that's I didn't emphasize it. That's why anyway. So let's recall what are the primary state. What's the detention of primary state? How did they find it? Do you remember? Okay, good. Can you act on whatever state, whatever operator O acts on 0? So that's what I told you. There's another way to define. So that's I told you. So that's the definition. One way to define. Another way to define. Another definition. It as follows. If you have a conformal transformation, so x goes to x prime is the conformal transformation. So the operator O I of x is behaved like this way. And then oh, sorry, this is J. So usually, if the operator or another conformal transformation, if it transforms like this way, then OI of X is primary. So I have to mention a bit of terminology here. So so this guy is a Jacobian. This is the Jacobian. And this D is the dimension of the space-time. And the delta is, of course, conformal dimension. Dimension of the OI of X. Okay. And then this one is a representation of the conformal group, conformal transformation. Okay. That's the definition. So for instance, if you just do the J mu nu acts on the operator OI of 0, we already knew that the distance is just S mu nu I B J or J of 0. And infinitesimally like this way. So this is the infinitesimal transformation. So that we already knew like this way. And then this R is the exponential, so the global transformation, which means roughly speaking, this one is the exponential of this whatever S mu nu. If it is a rotation like this of the and then so this acts on 0 here, But if it is a global, then it depends on x, then there may be some dependence on x here and so on. Anyway, so this is the representation. This is one way to do, another way to differentiate. Okay. So that's and if you take this, this is a global transformation and infinitesimal version. The Jacobian uniform. If you do the Fourier transformation, you have a Jacobian, right? Yeah, of the Jacobian of the x goes to x prime is a coordinate transformation or conformal transformation. So infinitesimal version. By the way, this one I already. So Anyway, so I keep updating overleaf notes. So this one I wrote around the section 5.2.4. Anyway, so you can take a look at that later. I mean, the reason why I wrote I keep mentioning, record my lecture and then write the detailed lecture note is for you guys to focus on the lecture instead of like looking at something else. Anyway, so no need to focus on taking so much all the note of the blackboard and so on. Just focus on what I'm trying to say. Well, what are the main point of the lecture? But anyway, so the new note I wrote this one in 5.2.4. And the infinitesimal version of this one is the QE. So this is the generator of this conformal transformation, and acts on this operator O I of x. So this one is the E dot mu delta plus del D. Okay, minus 1/2 del mu. And then j or j. Sorry, maybe I should write down this one. It's like this way, and then here you have delta ij. So this is the transformation. So how do you get it? So this one. So okay, maybe I should write down this one. This one is the infinitesimal version. It's something like this one. In my notation, this is 1/2 mu e nu and s e nu ij. This is the transformation rule. And then, so this is Jacobian of this one. Since it's a conformal transformation, so we already knew that in conformal transformation, so what was that? Del x e del x prime mu rho x mu x sigma g mu is the g rho sigma with conformal factor. Okay, that's what we already knew. And this one can be written like the proportional to 1 plus delta epsilon, some proportional coefficient. It depends on dimension. So that's so 2 over d. If you do plus order of reason. Like this. So that's what we learned from the long time ago conformal transformation. And determinant of this matrix, okay, is a Jacobian. Okay, determinant of this matrix is Jacobian. Therefore, this guy can be understood as the so this one can be understood as the 1 plus So since determinant and take us so the output dot e, and then am I correct? I think I told you wrong. So this is simply just not the. I think it's just 1 plus like this way. So to match with that one, it should be like this way. Okay. It should be like this way. And also this is plus. Sorry. Okay. So actually 1 plus. Yes. Down dot e plus order of e squared. Okay. So therefore, if you just look at how it transforms, it's just O prime of x prime. It's roughly speaking 1 plus e 1 minus roughly. If you only keep tracking of the full leading order of this one, 1/2 down mu in mu. S mu, ij, and operator over x. Okay. That's how it works. And if you take the difference between these two, what you get is this one. So E dot delta is essentially O prime x prime minus OX is the order. The leading order is this plus order of instances. Okay. So therefore, so the infinitesimal version of this transformation is this one. Okay, so that's how you get the infinitesimal transformation. Okay, now how you connect this transformation to the prime states. Okay. Okay. So recall that this is the special. So the K mu is the generator of the special component transformation. The special component transformation is given it's from mu of x is given by a mu x squared and then 2 times a of x squared. So that's the special component transformation. Infinitesimal versions where a is a constant. Okay. So that's the case. So now, if you just only look at the zero of this one, so and then e mu 0 is 0, and down of e also 0. Since it's quadratic here, it's quadratic, and this is cubic. So therefore, if you take x on the only first derivative, or it's itself, and take x goes to 0 limit, everything becomes 0. Okay. Okay. So therefore, if you plug this one into here and take x goes to 0 limit, so the k mu of all 0. Okay, and will give you epsilon of 0 is 0. So therefore, this term vanishes, and double epsilon is also 0. Okay, at x equals 0. So the right hand side at the x equals 0 is always 0. Okay, do you understand? So e is 0, right? At the x equals 0. Double e is also 0. And down of e is also 0. Okay? So therefore, right hand side vanishes. Okay? So therefore, you get the original definition. K axon O is equal to 0. Okay? But the global version of the primary field should transform like this. That's a global well defined the primary field. This is I didn't explain properly. Okay, so that's the one with. So now the question is why this is the case when d greater than or equal to 2. So let's recall. I mean, if you're very diligent enough, one can show that how the T mu behave under conformal transformation, and derive k really minus T mu. So, but you don't need to do that. So let's recall what's the definition of T mu. So the proper way of defining T mu is 1/2 square root G, and then del S del G mu. So that's a proper way of defining the stress energy tensor. Okay. So now the question is how it transforms under the conformal transformation. We know the square root G under the conformal transformation x goes to x prime. It's just a square root G behave like a del x prime del x. Okay. Square root G. That's we already knew. Okay. Because it's a determinant. Anyway, so that's the. I mean, if you don't know this property, you should learn the tensor calculus. So that's how it behaves under the metric to behave on the conformal transformation. Whatever any diffeomorphism, any coordinate transformation, and this square root G is take a determinant and then take a square root. So therefore, what you get is this guy. Okay, and this guy should behave like a delta S delta G mu should behave like it's transformed like I don't know which one should be the best way to define. Yeah, I think so that's how it should behave under conformal transformation. Okay, so that's how it should behave. So therefore, combining these two properties, one can show that so therefore, T mu prime and x prime should behave like this way. That's how T mu behave like this. And if you compare this one and this one, this is exactly the property of the primary state, how primary state should behave. So this Rij is the representation of conformal transformation. This is exactly the spin 2 tensor should behave under the conformal transformation. So therefore, what is the delta of the stress energy tensor? Yeah, so this is equal to dimension. So from here, what you learn is that the T mu is a primary of conformal dimension. Delta is equal to space-time dimension. So that's true what you learn. So this is, I didn't explain last time very properly. I just assumed that everything is, I mean, yeah, this is, so therefore any CFD, high dimensional CFD, T mu is a primary field. And the rank 2 symmetric traceless primary field. And this is a very generic property in high dimensional conformal field. Okay, and that's a difference between high-dimensional CFT and equal to two-dimensional CFT. That's I didn't emphasize it because it's very, very well documented in the methodology. And the infinitesimal transformation of this guy, it's easy to derive. So QE of T mu, it's also easy to derive. E delta T mu nu. I mean, this is a good exercise to do that. Delta E T mu nu, and then like this. So that's the infinitesimal transformation of the stress energy density under the conformal transformation. So this one is actually written in section 6.2 in the new note. I forgot to mention. I added. Sorry about that. Anyway, so if you use this property, if you use property for conformal transformation, the first term is really coming from first two terms really coming from just exactly this. When you set delta is equal to D, you get the first two terms. And then the last two terms is coming from this S mu nu. And to derive S mu nu from this whatever representation of the conformal transformation is not so difficult. I mean, you get these two terms essentially. Actually, there are four terms. Yeah. Or I added this spin 2 S mu nu part is appendix A. How to derive for spin 2 fields in a new note. I mean, I know. I mean, Chinese students really wants to know all the derivations, so I just derived this one in appendix A. But I'm not gonna give you in the detail, you know, on a blackboard. I mean, because it's just a detailed calculation. It's just waste of time. I mean, you guys just take a look if you're interested. Anyway, so that's the transformation rule, and there's the same reason. So that if you set that this is x, whatever, and if you set that x goes to 0 limit x is equal to 0, you get the k mu t mu nu 0. Okay, or roll. Is 0. As you can easily see that because of this property for special conformal transformation. Okay. Yeah, so that's one thing I wanted to explain. So now the primary field, important primary field. That's okay. So that's the one primary field in high dimension. Another primary field important the other important primary operator in CFT of D equals greater than 2 is the conserved current. Okay. Actually, this is also true for D equal to 2. D equal to 2. But I mean, we already knew that in D equal to 2, free scalar theory, del phi is primary. Is a primary. Okay. And in fact, this one is the current. is a current, and the transformation 5 to 5 plus whatever constant. Okay, so what's under this transformation? And let's derive this one. This one is also very easy to derive it. Maybe I can erase somewhere. So what is the conductor current? So the conductor current is what is the conductor current? So the conductor current is a net theorem stated. So they're given a continuous symmetry. The action is transformed as like this way. This action is transformed like this way. Okay, so that's and this is and then so therefore this should be converged. That means so this will give you that we already learned the beginning of the lecture. Okay. Now in CFT, this property is invariant, and this property is intact and invariant and conformal transformation in CFT. So what is the CFT? CFT is the under any conformal transformation, all the properties, the physics does not change. Okay, so therefore this property does not change under conformal transformation. Okay, so therefore, so the x goes to x prime under the conformal transformation. Del mu is just transformed like so that's how it should transform. Okay. So therefore, so J mu, so this part is intact. So therefore, if you take so therefore J mu is in fact transformed under the transformation self x prime x minus d minus over d, and then that x del x prime. How can I write it down? So mu of it should transform like this. Because double J should invariant under the conformal transformation. It should be equal to 0. And we know this is how it transforms. So therefore, J mu should transform like this. And then so from here, so therefore J conductor current is the primary. So you just behave like this way. Primary spin 1, okay, vector, spin 1 or vector, spin 1 or vector, primary of the conformal dimension is equal to d minus 1. D minus 1. I mean, if you combine them together, sorry, not one. Okay, so that's how you should transfer. Okay. So if you combine them together, this Jacobian will cancel Jacobian from here to become invariant under this transformation. So therefore, the conserved quantity is also the primary field in the CFD in higher dimensional CFD. So these two are the most important primary field in higher dimensional CFD: T mu and J mu. Fine. So, and let's recall what we have done last time, and then last time, so we think about the singular vectors, and then we just there's a type 1, type 2, and type 3 singular vector. And then we just need to recall what are those. And unfortunately, I didn't print out that part. Oh, maybe I did. Yes, I think. Sorry. Yeah, type 1 is just something like a p acts on operator is equal to 0. That's what we like. And then this will lead to the operator is the identity operator. Type 1 is boring one, as far as I recall. And then this one is essentially that if you have a symmetric trace lock operator, the sum of the p mu 1, p mu l acts on. So this will become 0. And this will give you some, in the case of, so this is R. I don't remember what kind of notation I used last time. I think last time I used R or something like that. R plus 1 and L. And then one of the example, special example is the conserved current operator mu and mu2 equals to mu L is equal to 0. So therefore, there's the conservation. So this one is conserved current, and in particular, one of the example is this one. Okay. So. I mean, equal to 0 means that the singular vector. So this becomes singular vector. And number 3 is the p square acts on operator is equal to 0. Oh. Okay, so that will give you the some prime model equation. Line model. So that was the number 3 we encountered last time. Okay. So yes. Okay. So that's the we encountered, and in this case, the operator delta of this operator should have d over 2 minus 1. Has to have d over 2. And then this is the free scalar field we encountered. In the case of number 2, I think so this operator should have control dimension is e plus L minus 2. This occurs in the that's what we derive. but from the Osborne's region. And we derive this one by index free notation. Free notation and so on. That's what we derived last time. But anyway, so what we encounter is essentially number one is trivial case. It's just vacuum. It's just singular vector is singular vector is the primary field, and primary field is the special primary field, which is vacuum. Number two is essentially will give you the conservation law, or partial conservation law. If you ask many times of P on this symmetric tensor, you get some kind of partial conservation law. Will give rise to the singular vector. Okay. Another thing is just equation motion. Equation motion for kind of equation. Okay, so that's the consequence of representation of conformal algebra. For that conformal algebra in D present. Okay. And then we think about the OPE in higher dimensional case. And then last time, so we thought about operator product expansion. And then that will give you rise to the lots of information of even the singular state, singular vector, and so on. Which actually I forgot to print out this part. Anyway, so the operator OI, so we essentially consider scalar primary OP of scalar primary. So OI of X and times OJ of 0, that will give you sum overCijk and Cx and IP mu acts on OK of 0, where K is a primary. Okay. That's what we, OK is a primary. Okay. Okay, and then, I don't know why, I forgot to print out this part, so I just need to take a look at my phone and so on. Okay, do you have any questions? And then, so we derive this one so this one can be constrained from the 3-point function. So the constraint comes from constraint from 3-point function and 2-point function. And in particular, we derive this, what was that? Yeah. So Cx tau mu, in the scalar case, we have this formula for something like this one. A plus A minus 0, 1 B alpha A plus minus 1 1 minus alpha A minus 1 and sum of m equal to 0 to infinity and factorial and the order plus 1 minus 0 over 2 and then minus 1 fourth x squared alpha minus 1 alpha del mu del squared e to the alpha x mu something like this. So that's the Osborne and McCarthy is result. And then you can just do the Taylor expansion of this guy. Taylor expansion. Expansion of this guy will lead you to integration of which will give you some ordered function and so on, and which I didn't explain last time very well, so I just think I should do that. So last time somebody asked you, so that will give you something like a delta plus delta 1, 2 divided 2 times n, delta minus delta 1, 2 divided by 2 divided by b. I mean, this part is not so important. I mean, this part is the Euler-Beta function. But gamma function is, this can be written in terms of gamma function, delta plus delta 1/2 divided by 2 plus n, and gamma delta, and then gamma delta plus delta 1/2 divided by 2 delta plus n. Okay. And last time I didn't explain very well. So essentially, what the pole comes from here. So pole comes from here when the so you can use the fact that the gamma delta is, what was it? Plus n is the delta plus 1 delta is it correct? So last time I sent you a WeChat message. Okay. Yeah, this is correct. Okay, so therefore from here this yellow part will give rise a pole at delta is equal to 0 minus 1 minus 10 plus 1. Okay. So that's really the pole coming from here. Okay. And this is exactly the place the singular vector arise when under this conformal dimension. Okay, so OP quotient, so OP divergence of E of OPE predicts the existence of the singular vector. Okay, that's the okay. That was our main message I wanted to convey last time. Okay. Any question at this moment? So yeah. So the pole is really coming from this part. Okay. Any question? Okay. And then if you use this OPE will tell you that this, if you have a correlation function O1 of x1, the total of n of xn is a correlation function. If you consider correlation function, we can just use apply OP 1 to k x1 minus x2, and this derivative comes in this one, and then OK of x2, O3, x3, OL, xn, like this way. Okay, so you just apply this to O2, x2, and you just apply OP here to get this one. Okay, and then you can do the multiple things. You can do the OP here or whatever here and so on. You can keep applying the OP here. That will determine that from there, one can determine correlation function. Essentially in CFT, correlation function are determined by this delta I conformal dimension, delta I, and then 3-point structure constant, CIJK, and also OP there. Okay, OP data will tell you this. This one. So this one is OP data, and that will determine. So in principle, determined by this. So. Okay. So therefore, and in fact, so these two are called conformal data. People call conformal. So without knowing any whatever Lagrangian and so on, at least if you know these three information, one can determine the correlation function in principle. And in fact, this OP data can be determined. So this one, this one is also can be constrained from the 3-point function, 2-point function, right? 3-point function, 2-point function. So that's what we did. We just do the Taylor expansion and so on to determine this OP data. So therefore, in principle, if you know that these two, one can determine the correlation function. In principle. So that's why it's called conformal data. Any question at this moment? Okay, so then let's apply, let's give you one important application of this OPE. Which is conformal regulation theory. So this is essentially the answer of one of the homework in the last problem in the last homework. And let's learn the application. Okay. Okay. So conformal perturbation series, you just consider the perturbed theory like this way. Okay. So you just perturb the theory like this way. And A is the scale of the system. A is the scale, so length, the typical, the smallest length you can resolve. Okay. So if you only look at the things from the light, then this A is the length of the electromagnetic waves. So the frequency is called. So the electromagnetism is something short. A is just this length. That's a scale of the. So OI is the some operator in control dimension delta I. So therefore, this one is the GI is the dimensionless. Dimensionless. Let's cover. Okay. So this guy is, so suppose this one is the conformal. And you perturb the theory by this operator OI, okay, with the control dimension delta I. E minus delta. So, okay, so this has conformal dimension delta I, so therefore this cancel with minus delta I in denominator. So therefore, so GI is dimensional coupling constant. Okay. Let's consider. So this is the action of this one CFD, and you perturb the theory. And consider the partition function. And the partition function is of course the V is the order field e to the whatever IS. Or minus S, depending on the Minkowski or Euclidean, and this one always given to like this one. And then they just do a Taylor expansion. ddx ddy divided by A 2d plus delta I delta j. Then gi gj or yx or jy and plus. So that's the Taylor expansion I did. I just put this one into here, and then do the Taylor expansion in the perturbated part. Here. Oh, okay. Sorry. I think I should use the Einstein convention. So the I summable operator I. Here. 0 means the correlation function by using the original action S0. Okay. So you just put that. So the O whatever O is 0 means the D. So the zero, and so this is the zero. Okay. In the subscript zero, because I mean we just keep this as zero and then do the Taylor expansion of this perturbative part. So you have to put the subscript zero here. So now and then we just do the same. So. We do the same coarse grain. Grain. Yeah, essentially what we need to do is essentially integrate about the pi momentum space, and then we integrate over 1 over a k, and then what was that? So that's what we are going to do. Coarse graining is that you just integrate over the. If you go to the momentum shell, we just integrate over all the field with moment that has. This is the A, and then this is the 1 over A, and 1 over A, 1 plus that. Okay, so that's what we are going to do. And under this scaling transformation, then you can easily see that the so this GI, so the classically, so if you're under this scaling transformation, so under the scaling classically, so this is we already learned classical scaling is GI equals to 1 plus delta L GI, and then power is the GI, and the power is D minus delta I. Okay? So like this. So therefore, if the delta I is greater than D, so this becomes the less than 1. So it becomes irrelevant. And delta I, relevant. Woo-hoo. So we already learned even 2D CFT, so this is the case. I mean, this whole quantity is this whole quantity is greater than 1 or less than 1. Okay. So this yellow part is if less than 1, that the coupling constant becomes smaller once you do the coarse grain. So therefore, if you go to the IR, so there's a low energy limit, this term, so this coupling constant becomes smaller. So therefore, you can ignore this perturbation. On the other hand, if this coupling constant is greater than becomes bigger, so this yellow part becomes greater than 1. If you do the low energy, becomes this coupling constant becomes bigger and bigger. Okay. So therefore, it becomes relevant. And then when delta equal to D case is conventional, then you have some special treatment. Okay. And then now I can rest. So now let's apply. So this is classical scaling, but if we want to know the quantum scaling, quantum effect to this scaling transformation. Well, So to do that, we look at this. We focus on this. Okay. And here we have a two-point function. And we want to just incorporate into the one-point function. To do that, you just apply p. So we know the OI of x dot OJ of y is sum ofCijk OK of y divided by x minus y, where k is a primary. Or some operator. So, okay. Okay, so this is OP, and then plug off into here. So this orange part. And this orange part becomes like this one, like this. So therefore, if you apply this one into the orange part, and this will become sum of k 1/2 Cijk. So A delta k minus delta I delta j. So I take x minus y is roughly k. So I just want to do the following thing. So I just want to integrate 1 plus delta L, and then so roughly you can approximate x minus y is a. Okay. Then ddx like this. So this orange part. The orange part is this. Okay. And then here, so integration of y. So integration of y is just applied by this region. So this is the integration range. So we just apply this one. And this integration range is coming from. Here, you can do the integration, use the, essentially, so ddy will give you d-dimensional sphere. With thickness delta L. So delta thickness delta L. So therefore, this will give you the following thing. So this will give you wait. I think I need to include this Gij. So this one I need to Gij. Okay, so that's the okay. Fine. Okay. And this integration is just will give you the factor of the SD times A to the D, and then delta L. Delta L. Thickness. So where SD is the volume. of the unit sphere in the d-dimensional. Sorry, what I'm doing here? I got confused. Oh yeah. It's not d-dimensional sphere. D minus 1 sphere. Sorry. D minus 1 dimensional sphere. With thickness the A times d delta. A times delta. Okay. So that will give you the volume is like this. So the SD is the volume of unit d minus 1 sphere. S unit SD minus 1 sphere. So sorry, this upper means the sphere. Okay, it's a computed volume of d minus 1 dimensional unit sphere. Okay, so that's it. So and essentially A times d minus 1 will give you the essentially anyway, so this is the with thickness of a delta, and if you plug them into here, what you get is that essentially the if you incorporate this one and then this one and massage everything, net effect you will get is GK is mapped to GK minus 1/2 SD sum of IJ Cij K. Let's use the Einstein condition. Cij Gi Gj delta. That's the net effect you get. So it's coming from using OPE here, you become one-point function. So therefore, you can incorporate it into the leading order here. But when you incorporate that one, so you need to take into account this part plus this part. Okay, all the A will cancel. So delta I, delta J will cancel with this guy, and delta K become a minus delta K, which is the same as here. Minus K here, and 2D here cancels the AD here. That will give you D here. Okay. So therefore, net effect becomes like this. So therefore, this is a quantum effect. If you use OP. And that's exactly what you need to do for the homework in problem 2 of the last homework. I think it's just almost unfair. We just continue to unfair. So dg k divided by dl, you have a classical scaling of gk k. And minus 1/2 SD Cij Gi Gj plus order GQ. Okay, that's this. Okay, so delta if delta is very small, this guy is a classical scaling. That is the leading order here. And then the subleading order is just coming from OP. Okay. OP. So that's the quantum correction you will get. Okay. Then we will apply this method to the action is something like this one. Minus dx. And then 1/2 like this. apply this one into the 5-4 theory. Okay. Yes. So this is essentially beta function. Beta function. This is essentially beta function, and then we apply this OP method to the 5-4 theory when you set d is equal to 4 minus epsilon. So this is the what Wilson-Fisher did. So we start with free field. So this is your S0. This part is your S0, and this is perturbation. So perturbation term, and the question is whether we can encounter something non-trivial. And you compute this, what was that? This beta function for both m squared and lambda, and the question is whether you can find something interesting. That's what Wilson-Fisher did. And I think to explain that it takes time, so let's take a break. So if you have a question, just tell me. So let's take a 10 or 15 minutes break. Otherwise. A to the D. So essentially, there's a sphere, right?
Yeah.
Sphere, and then the unit sphere have a volume have a SD. And this, since if the radius is A, you have to multiply A D minus 1, right?
But SD is superior, which lambda.
Not the what?
The average.
So this sphere with radius A is A to D minus 1, right?
You know the volume.
Yeah, volume.
The volume, but volume.
The sphere, or like the area of this sphere is A to the D minus 1, right? And we want to do the so we just want to integrate out this region, which is the thickness is the A times the outer L. So therefore, if you multiply them, you get this one.
Yes, maybe. Then this is the A to D minus 1.
Yeah. So the area is A to the D minus 1, but you need to consider thickness.
I have a question about the regulation. So here we want x and y cannot approach closer than a. And here I want the point splitting freaks to splitting variance and not useful for each series. So are we in situations
Yeah, so that's why I put this constant. X minus y greater than A. So this is your epsilon.
Yeah.
So X and Y cannot approach less than A. So I put some lower bound. So it's okay, right?
But he says it will break translating. I think
this is also break translation. In practical cases, it's useful as opposite. Okay. Widespread translation.
就是代表它不是连续的那个平衡数。然后这个没关系，这是一个关系。
这里说，这里才
它就不是那个，它就不是那个。
这里是不是？
这不是，这个就是一个 cross 而已。
但如果我用那个 S， 它有一个，它是一个。
这个东西它是一个，就是把它那个cross 可以就是它把那个动态这个基到这个给它设一个基本的上这个就是说把它给设一个这样子的一项的方式。就它不是考一个假例子，它是把那个它假设它有一个上限。它实际上是它是多来的上限，对，它对应的一个定义。
但这边就是我们
不，它这只是区别那个上面在这个上上。
What is the meaning of primary key is 2D? So you have infinity.
它是两回事。
The primary key, primary state is whatever. H is equal to 0, n greater than 0. That's in 2D. But in high dimension, we only have L1, which is K, essentially. So therefore, that is a more important.
So
yeah.
Is it just
Yes.
Why D equal 2 is a special case one我想的是为什么刚才那种是T的用词是特殊的 ，Why T in D equal to is special.
So if you look at the OP of this, it's equal to Z4 plus whatever Z 0. No, that's important. Sorry. 2T. And this is Z.
Yeah.
This is actually action of this L1 TT. The L1 banana is T0. Equal 0. But the L2 action will give you something non-trivial.
Yeah.
In 2D, you have infinite many the Ln to define the primary key. But in the case of the higher dimension, we don't have L2, L3, we only have L1.
Yeah. But I'm wondering, according to the procedure we do in high dimension, we do not need L1.
Yeah. With higher dimension, that's why there is a difference between higher dimension and 2 dimension.
Yeah, I know this difference, but I don't know why according to the C procedure we cannot get T mu is primarily D equal to.
Because I mean, D equal to conformal transformation is infinite dimension.
Oh.
Yeah, algebra is different.
Yeah.
Yeah, I understand what you mean by what you say. Or here. let me buy something to drink. Yeah, now I understand that why it breaks the translation, but so since we just do the code, like essentially we just put the theory on the lattice with the side A, like with the length A.
Yeah.
So this translation, this kind of like a over 2 translation, or X is translation X plus C, where C is less than A. This will break the translation invariance. That's why if you put the lower bound like this way, that will break the translation invariant. But that is okay. That is okay because I mean this is the usual scheme to do the regularization. And also it's not gauge theory here. This is so we are just considering some CFD, which is not the gauge theory, so it's okay. But the reason why if you put the lower bound for how to say to operator can just how to say approach, because I mean if you do this kind of transformation that will break the translation. I think that is not the issue.
就像你
question?
We know that D is equals to is a special case.
Yes.
So if we consider like D is one of D is smaller than 2, are they also special case?
D equal to 1.
It may be true, but I perhaps the question is D equals to the only special case?
D equal to 2 is a special but interesting. Because when the conformal algebra gets enhanced to infinite dimension.
Another question is T mu mu is also a concept.
Yeah, concept.
I mean, yes, concept.
Yeah.
So, you mean another important analysis is constructed current.
Yeah.
Not T mu mu.
Yeah, so
It contains the T mu mu or
I see what you mean. I see what you mean. Let me think. Good question. Good question. answer to your question. I'll think about it. I don't have a good one. I think it's really classical. Okay, so maybe let's resume. So his question was as follows. So okay. Maybe one way to explain is the way we derive the singular vector for conserved current. So his question is T mu is also conserved, but the T mu is a primary of the conformal dimension D, whereas so what I mentioned is the J conserved current is always the primary of the D minus 1. And where does this difference come from, the conformal dimension? Even though this way, the T min itself is the conserved current. That was his question. The one way to answer is really this way. This way is only D minus 1 only for spin 1. So this is only for spin 1. So therefore, you cannot apply this directly to here to this one. As I mentioned, number two, singular vector appear and in this way. So the O mu, mu1, mu2, mu L. So this becomes singular vector when delta is equal to D plus L minus 2. D plus L minus 2. And this singular vector literally means that this is the conserved quantity. Okay. So when L is equal to 1, this becomes D minus 1. And then when L is equal to 2, this becomes delta equal to D. So therefore, the conformal dimension, even though it's a conserved quantity, D mu is conserved quantity, since it's a spin 2, so the conformal dimension should be D. Anyway, so that is another way to see the difference. Yeah, I think one way to answer to his question is the spin is different. That's why the conformal dimension is different. Even though both are conserved current, but what I meant is here is the really spin 1 conserved current. Okay, so that's maybe one way to answer the question. Is there any better way? Okay. Now let's do the Wilson picture. Yeah, Wilson picture. Fine. So what we want is to do the. So this equation, where is it? Oh yeah, I already erased. So what we want to derive is this equation, d gk dl is equal to this one. So for this action. Okay. And now gk is actually m squared and l lambda here. Gk is alpha. And then we want to do the, so what is the dimension of m squared? Or phi squared, what is the dimension of conformal dimension? So this is 2 and this is 4 conformal dimension. But now also here, what we want is these. So this we want to apply this epsilon prescription. This is what the Wilson just considered. The reason why we introduced this epsilon is that we often use this one as the dimensional regularization in QFD. That's one reason. The other reason is that when you set the epsilon to be 1, you go to 3-dimensional. Even though, usually if you do that, this is epsilon prescription. Epsilon is treated to be very small. But that would sometimes tell you that even if epsilon goes to a very big quantity, sometimes tell you some insight. So therefore, there's two motivations. One is the dimensional regularization coming from quantum Q theory. The other is really coming from the changing dimension. That's what Wilson. So therefore, in this case, if this is the case, what's the dimension? Del phi, scaling dimension of del phi is the 2 minus epsilon divided by 2. Okay. So that's a scaling dimension. So therefore, del phi squared, classical scaling is 2 minus epsilon. Del phi 4 is 2 times 2 minus epsilon. Okay. So that's the classical scaling. This one. And now we want to see the OP this one. But this one we already did in the OP in free theory. That we already know phi squared x1. Yeah. This one we already did many long time ago. Not long time ago, like 2 or 3 lectures before. It's just with contraction and then the normal. If you use this one, there's a way to 2 way to the 5, 5, 5, 5. And then this way, and with contraction this way or this way. And then that will give you the 2 times C. Okay, so that's the OP of these 2 operators. So we treated these operator. Okay. So the second term comes from the like this one. And there are many ways of doing that. There are many four ways of doing that. This one. Yeah, this one. Well, that's why you have a 4 here. Sorry, I'm getting tired. So, anyway, let's do that. No, I'm just getting old. 5 squared x 1, that's 5 to the 4 x squared. Let's just do the same thing, same exercise. What you get is like this way, 2d times 4, 5 squared of x2. This one you already also know, right? 5, 5, normal, and then 5, 5, 5, 5. Yeah. And then there's a 4 way of choosing this. And then once you pick that one, you can take the other 3. So the 4 times 3 will give you 12. Okay? 4, 12. And so on. And the other thing is 8. this one, there are lots of them. 24, 34, x1, 2, 40 minus 8. I mean, this is just a really straightforward calculation. C3, x1, 2, 3d minus 6, 5, 2x2, plus 72 c squared, x1, 2, 17 minus 1, 5, 2, okay, so that's what. Those are OP of these two terms. So I treated this guy as O1. I treated this as O2. Okay, and this is the G1, and this is G2. Okay. Okay. So those are OP. So how do you get this 24? No, I just try to check whether you are awake or not. How do you get this 24? 4 factorial, good. Because I mean it's 5, 5, 5, 5, OD, 5, 5, 5, 5. There's 4 ways of choosing that. Once you do that, the next one is 3 way of choosing that. And the next one is 2, and then so there are 4 factorial. 96, I will give you the exercise. It's not so difficult. Anyway. So all those things can be just determined OPE. So now we'll just plug into this formula. Okay. So these Earths. So let's see. So this one is the what? This one can be treated as C111. Okay. I call it this one is operator 1 and this one is operator 2. So therefore this is C111. And this one C112 is equal to 1. Okay, do you understand what I mean? And then here, this quotient is what? C. What's the subscript? Good. C121. And so on. This one is the C, and what was it? 1, 2, 2, and so on. And plug that one into here, and just write down the renormalization group flow equation. For beta function equation. Fine. Okay, then plug that into here, what you get is as follows. Okay, C lambda equal like this way. Okay, so like this way. Okay, so the trivial solution is of course if you solve this one, m squared is equal to 0 and lambda equal to 0. That is the just free theory, free CFD. But non-trivial one will be given as follows. If you assume the so m squared is given by order of epsilon squared, Okay. And then plug down into here. Well, non-trivial solution can be obtained by just looking at this one and this one. Non-trivial solution means the fixed point. So, as I mentioned, so fixed point. So this is a beta function. Beta function. Okay. So therefore, the fixed point is always beta is equal to 0. Okay. So the CFT at the CFT point, beta cannot be non-zero. Okay, because I mean, if you do a scaling transformation, beta shouldn't be. So scaling CFT, the physics does not change. But if beta is non-zero, if you do the scaling transformation, coupling constant will change. So therefore, the physics will change. But if beta equal to 0, it's scaling invariant, which implies CFT. So now also we want to solve this one. So the epsilon lambda minus 72 square lambda square times what was that? 1/2 SD is equal to 0. So this is d lambda dl. And this will give you the fixed point is lambda is equal to epsilon divided by 36 SD C squared. Okay. Okay, so then we want to okay, that's the case. No, sorry, I just got confused. Why this is 2, to be honest. So this should be delta minus d minus delta k, right? And then, as I mentioned, delta phi is equal to 2 minus epsilon, right? So it should be 2 minus epsilon. Because we will consider 2 minus epsilon. Thank you. Thank you. Thank you. So d is equal to 4 minus epsilon. Yeah, and epsilon tells. Thank you very much. That is equal to 2. Okay, and about so phi squared, phi to the 4. He's much his brain is much more working. 2 epsilon. Okay. So therefore you get 2 seconds. Okay, thank you very much. Thank you. Thanks for correction. Okay. And then plug this one into here, and then just looking at the leading order term of epsilon. Okay. And then, so the plug this value into here, and then only look at the leading order. So that is only coming from here. This is E square will give you here, E square will give you here. So therefore, what you get is dm square d lambda is equal to 2 minus 24 divided by 72 epsilon m square plus order epsilon to the square. Okay, so that's what you get. What is 24 divided by 72? Can you simplify it? Okay, good. This is 1 over 3. 1 over 3. Okay. 70 is coming from the, what was that? 2 times 36 is 72. 2 times 12 is 24. Okay. So now, this delta of phi square is the so as you recall, so there's an LG minimal model correspondence in 2D. Okay, and then so P equal to 3. We look at the P equals 3 and P equals 3 corresponding to Ising CFT. And that will be coming from London model. Now phi square plus phi to the fourth. Phi to the fourth at the most. Okay, so that's the London model we consider for in 2 dimension. I don't remember the question here. 1/2 maybe. And then here should be 2 times P minus 1. Should be 4. Okay, good. So the pi 4 theory will give you the Ising CFT. That London model flows to Ising CFT. That's what the Zamochkov taught us. So this is a 2-dimensional version. But in 4-dimensional version or like high-dimensional version, we expect a similar thing to happen. And the difference in pi 4 theory is also expected to be related to somehow Ising CFT. And then here, we know that there is a non-trivial fixed point. So this is the so this is a trivial fixed point. So this is called trivial fixed point. Fixed point. So which means the theory is free. It's free. So this is a non-trivial fixed point, or Wilson-Fisher. So people often go, this is a Wilson-Fisher fixed point. Because Wilson-Fisher concept. So when dimension is d is equal to 4 minus epsilon, and then this one is the transition is so interacting CFT. Interacting means the theory is not free. There is some interaction among the field and so on. Okay. And then this is the Ising CFT in the correspondence between so here we look at the Ising CFT, we look at the so 1, 5, what was it? I already forgot to put my previous lecture number 1, 2, 2, 1, 3, 3. 1, 4, 4, and so on. So, but in the case of the Ising CFT, this one is C. And then that will corresponding to 1, 5 square, 5 square, and then 5 cube, 5 to the 4th, and so on, as far as the result. Yeah. Yeah. So we have this kind of correspondence, right? I already forgot the 2 one. Sorry, I should have known that, like this one. Is that the... But sorry, I mean CFT, there is no 533, right? Does it? Sorry, sorry. What's Ising CFT? So Ising CFT is the so we pick this one is the point of this one, and these are primary field, and 1 sigma epsilon, something like this one. And then most likely it's sigma 1 epsilon. That should be the case. And then what we need to identify is the, okay. So in the Lagrangian correspondence 1, 5 square. 5 square I cube 5 is it the case? Most likely no. Do you have a lecture note on my lecture note? Anyway, I'm sorry. But anyway, if you have this correspondence, phi square should correspond to epsilon. So that's the energy density operator into the. So therefore, this one is expected to, phi square is expected to somehow related to the, I think CFD is the epsilon, the energy density operator. This epsilon is different from this epsilon, okay? So this is the energy density operator, okay? And then in lambda equal to, I think CFT corresponds to phi square corresponds to epsilon, okay? Anyway, so then the dimension of this guy is 2 minus epsilon minus plus 24, 1/3 epsilon. Okay, so that's the from this analysis. So therefore, if you write down the critical dimension, so this critical exponent of phi square is given by d minus 1 over nu, and then this nu is called critical exponent. In static dynamics, critical exponent. And then if you compare between these two, so nu is equal to 1/2 plus epsilon 12 plus order of epsilon squared. That's how you obtain the critical exponent of the 5-volt theory in D is equal to Conformal section. Okay. And similarly, you can just obtain the calculation of the delta phi and so on. So that should corresponding to the. So I think most likely, so in the case of lambda correspondence, most likely what we have is the 1 sigma epsilon 1 epsilon, right? So therefore, okay. Sorry. So then what's corresponding to phi square? That's the correspondence. So phi corresponds sigma and phi square corresponds epsilon. Okay, that's what's happening. Sorry. Now then it's okay. So therefore, this del phi corresponds to del sigma in the Eisenberg. Okay, and then you can do the similar calculation. And then this will give you the following thing. Maybe I can write down here. So del phi corresponding to del sigma. And this one will give you corresponding d minus 2 divided by 2 plus 8 over 2. And this is a critical exponent again. Critical exponent. And then in the case of the x, so this is the Wurst-Fischer point. This will give you minus epsilon divided by 2 plus epsilon squared 108 plus order of epsilon of k. Okay. So therefore, if epsilon is very small, critical exponent is say the epsilon squared divided by 54. Okay. So that's the critical exponent. In D is equal to 4.6. And then the original motivation of Wilson Fisher is that they wanted to take the epsilon goes to 1. Now, of course, this perturbation theory breaks down because when you take epsilon goes to 1, this term will become important. This sublinear term will become important. But that will give you some insight. So even though this epsilon prescription cannot simply apply to this limit, but that will tell you that there is some non-interacting CFD who exists when you set this dimension. And then that would suggest some suggestion, some hint to the 3D Eisenhower. So the 3D Eisenhower is so the Wilson Fisher, the original motivation, when you set epsilon goes to 1, that will describe the Eisen CFD as a Wilson Fisher point. Okay. Although those values cannot be simply applied for critical exponent or 3D Eisen CFD, but this would imply that that's I wouldn't say 3D Eisen CFD. So this has 3D Eisen CFD strongly suggests that have 3D Eisen CFD. Eisen model is described by Conformal. That's the people's expectation. Nobody proved it. Nobody proved it at this moment. In fact, two-dimensional Eisen model is exercise CFD. It's proved by Smirnov, actually, and who got a fifth now. If you solve this one, if you just give you a rigorous proof of this one, most likely you will get the fifth now. Okay. Anyway, so that's some hint to the 3D Eisen model from Wilson Fisher. Any question at this moment? Okay. If not, before going to my original plan was going to the Conformal block, but I think I should tell you something about two-point function, three-point function, higher spin field. Or primary field. So we put in here the T mu nu and J mu higher spin primary field. And I didn't tell you anything about the two-point function, three-point function, higher spin primary field. So I should explain it. And unfortunately, I only have 3 more lectures. My plan was to tell you something about conformal bootstrap about 3D Eisen model, which is the spectacular result in that was occurred in almost like a decade, only 10 years. It's very recent. I don't think I have time to do that. But anyway, I'll try my best. Conformal bootstrap and so on, but I don't think I can explain very well. But anyway, time short. Okay, so we know there's a two-point function. So now the two-point function is three-point function of the with higher spin primary field in So now I think I should talk about this one before going to the 4-point function. Unfortunately, I have to talk about it because the 4-point function is a much more difficult 2-point function. And this one I wrote a new section. So section new note 8.2, so section section 8.3. And then 8.3 is using word Takahashi identity, and then 8. Yeah? No, 8.3, sorry, 7. Sorry, 6.2. 6.2 and section 8. And then you note derivations. Yeah. So 6.2, just derive this by using word Takahashi identity. Takahashi identity. Identity. In Chinese, like this, as for the and this one is the something called embedding. Higher dimensional space and what is it called? I don't remember the details. Embedding method? Embedding space-time format. Embedding space method. This one is okay. So that's I wrote a new note in the two way of deriving this 2-point and 3-point function in new note. This one is very easy, handy. This uses the symmetry of correlation function. I mean, this is standard method. This embedding space method is I think it's very relatively recent, like only like 10 years ago, 15 years ago, something like that. 15 years ago, something like that. By Lichkov and the company, as far as I don't know, maybe Simon Duffin. I think I cited the proper reference in the introduction. And using two methods, we derive 2-point function and 3-point function for high speed. Okay, let's use the word Takahashi identity in last 25 minutes to derive this 2-point function. Okay. So now I just want to derive this something like J mu of x1 and J mu of x2. So this 2-point function, where J mu is the spin 1 parameter. That's what I want to show. So the method is usually very, very simple. So using the conformal translational invariance, so translational invariance we call it that. So this one, or maybe this one, is the is equal to translational invariance will tell you this is equal to x1 minus x2. That's a translational invariance. Okay. And another thing, scaling invariant. Scaling invariance will tell you that this J mu of 0 and J mu of x is given by x delta 1 plus delta 2 divided by 1 J mu of 0 and J mu of E is the unit vector. Any place is okay. Okay, so that's the case. And what's left is can be determined by something like special conformal transformation and rotation. So we have to use this special conformal transformation and then rotation to fix the so essentially what we need to do is J mu of 0 and Z mu of EV is equal to, sorry, I think I should use this x hat actually. X hat is equal to 1, but this is x hat, and then this one is equal to so R, let's see, sigma mu of 0 or mu rho of x hat of j sigma of 0 j of e, where e is equal to literally unit vector, like whatever unit vector in d dimension, even like this. So this is the representation. These are representation of the conformal transformation. Conformal transformation. That's what the word function identity will tell us. And now what we want is as follows. Let's consider the following thing. So the special conformal transformation always involves, so as you recall, there's a unit sphere, and then what you need to do is the inversion of this one, and then translation and inversion. So that's a special conformal transformation. Okay. So that's the, and then so. If you pick the translation to be 0, it's just an inversion. So inversion is just an x like this. Okay. Inversion is like this way. So x mu. Okay. And now we want to fix the something combination with the inversion and rotation involved. Both two of them and to fix 0 and e. So 0 is here and e is here. Okay. Essentially e is here. We want to do such a transformation which is easy to in fact achieve that. For instance, you can do the following thing. So the x prime of x is the inversion e plus lambda inverse h I of x minus e. So this can be the 1. So this is the scaling transformation. This is rotation. Okay. Let's look at what's going to happen. Let's set x to be okay. I of E is E itself, okay? Because I is inversion on the unit sphere, so E is fixed on an inversion. E minus E is equal to 0, okay? E minus E is 0, so therefore this way it becomes around the rotation. H is the rotation around the E, so that's what it means. Okay, so therefore, so this one is fixed. This is still 0, and this scaling transformation around this one is still like the origin is fixed. Okay, so therefore, And this is essentially, so that this is E, and this becomes 0, and rotation, 0 of rotation is 0, scaling transformation of 0 is 0, and plus E is the, just E. So therefore this is equal to 1. Okay, is it okay? So, yeah. So essentially E is moved to 0, and the rotation and scaling transformation does not change anything, and it moves to E. That's what it did. Let's look at the x prime of 3. 0 of inversion is this become infinity. I of 0 is infinity. So inversion go to infinity. Infinity minus E is infinity. Okay? Rotation of infinity is infinity. Okay? And scaling transformation of the infinity is infinity. Okay? And even if you shift the infinity by E, it's still infinity. But the inversion of infinity is 0. Okay? Therefore, this is 0. Do you understand what I mean? So essentially, the first transformation will go to infinity. 0 goes to infinity. Whatever transformation do to infinity is still infinity. And at the end of the day, you get the inversion. So you get this. So therefore, this transformation involve inversion and rotation and scaling transformation, but it fixed 0 in E. Okay. Let's apply this transformation to this the correction function. The important thing is that the so to see the infinitesimal transformation, you take a derivation of this I by x. So x nu by x nu. Okay. So if you do this one, then this is just given by as follows: 1 over x squared delta mu nu minus 2 times x nu x squared. Okay, so that's the infinitesimal transformation. It's derivation of this transformation, and we call this one is equal to I mu. We define this one as mu of x. Okay, and then so this transformation rule will tell you that the shift doesn't matter because the shift, the correction function is invariant on the translation as they already knew, and the scaling relation will give you just conformal dimension, and the inversion of the rotation we need to do the some transformation rule, okay, so that O J mu of C and then J mu of epsilon is in fact given by lambda, and you just apply this transformation for fix 0 and E, so therefore that will give you that one, so the J1, J2, delta minus delta 2, lambda minus delta 2, and then so here you get the H of mu rho, and then here I-E, H and I-E of mu sigma and then J, rho of kilo, and J, what was that? J sigma of epsilon, like this. So here it's a representation. H is this action on the operator on 0. Okay? So the inversion does not do the anything on the operator or at 0. So therefore you can ignore I here. On the other hand, for the position on the E, you have action on I and H and I. So the translation does not do anything. Okay? And the scaling transformation is overall scaling dimension is coming here. Okay. So therefore this correction function will satisfy this identity. IE. So now IE is the I whatever mu of E. So this guy is this. And then this one, if I write down this one to be sorry, I got confused. Yes, I think roughly speaking what we are doing. Sorry, so we are only looking at the. We just get rid of this one. Okay. Lambda. I'm confused. I think I'm doing something wrong here. No, I'm just wondering what should we do? Okay, we can set the lambda to be 1. Okay, so let's set the lambda to be 1. Yeah, let's set the lambda to be 1, and then let's call this one to be y mu. Okay. So then what you get is that the y mu is h mu rho and y rho sigma, and then I-E, H-I-E, and then mu sigma. Okay, so that's what you get. So from here, what you get is that essentially, if you write down this one as the matrix, this is y is equal to h, y, I, E, H, I, E transpose. Okay, so that's what you get from this equation. And then from here, what you get is that the H times Y is the H transpose is Y I E. Okay, so that's the transformation one can obtain. So IE is a symmetric matrix, as you can easily see here. So IE is essentially this delta mu nu minus 2 mu E nu. So this is a symmetric matrix, mu and nu. So transpose does not do anything. And then I E transpose is I inverse. E. Am I doing correctly? Transpose. No, I is self is I inverse. Let me check. I square is equal to delta mu minus 2e to mu delta mu rho. Sorry. Minus 2e mu e rho. And then this will give you delta mu rho. And then here what you get is minus 2e mu e rho. Sorry. And this is the multiplication. And next is this multiplication. It's minus 2 e mu e rho. And it just multiplies these two plus 4 e mu e rho. Okay, and they count out, get delta mu. Is that okay? So I square is equal to identity. Okay, is that okay? So therefore, so square is equal to identity. So that and the IE transpose is IE. Okay, so that's you can check this one. So from there, you can derive to this one. So this means that the YIE is the invariant on the rotation SOP. So this H is a rotation. The rotation SOD. Of SOD. Okay, so that's for. So this means that the Y is in fact proportional to IE. Y inverse, which is IE. Okay. So therefore, this means that the B, not B, J mu of 0 and J nu of B is some constant times some constant. I call it let's see, 1, 2 times the IE mu nu, which is the delta mu nu minus 2 e mu e. Okay. And if you use this scaling transformation, what you end up with as follows. So J mu of 0, J nu of x to 1 is 1 over x1 2 delta 1 plus delta 2, and then C1 2, and then I mu of x, where I mu of x is equal to delta mu minus 2x mu 2x nu. So that's the case. Okay, so what you obtain from this Okay, any question at this moment? And unfortunately, I think I made a mistake. I think some of them should be, either of them should be plus. I don't remember. I think I followed this Simon Duffin's lecture note. I cited as Simon Duffin. And then from there, I think even though you don't set lambda equal to 1, you should get this condition. You should get this condition. It should be invariant on this one. So I think I made some mistake in sign here. So therefore, this will the imbalance of this transformation will tell you delta 1 should be equal to delta 2. So therefore, in fact, this one should be 2 times delta. I think this one, I'm pretty sure I made a mistake in somewhere. Next time I will correct this. I think I made a mistake in some sign here. I'm pretty sure that's the case. And then both, so that conformal dimension of these two primaries should have the same conformal dimension. That's the same as the scalar case. But if you have a spin 1 field, you have extra pieces coming here. So that's the spin 1 primary field case. Okay, so that's the So what we need to do is in scalar case, we just have I think I made a mistake. In scalar case, or 1 of 0 or 2 of x is just x to delta and some 1 to something like this. And the delta 1 is equal to delta 2 is equal to delta. I mean, this should be the same as here. Should be the same as here. But somewhat maybe my lecture note is some mistake. I will correct next time. So in any case, in two-point function, even spin 1 case, both primaries should have the same conformal dimension. Otherwise, it'll vanish. It'll vanish. I think derivation should be the same. I think I made some mistake in somewhere. Let me check where I made a mistake. Yeah. No, I don't know where I may make a mistake. I think the previous case we used special conformal transformation to show delta 1 is equal to delta 2. So here, somewhat I don't. Anyway, I'll correct next time. Anyway, so that's a conclusion. So spin 1, the primary field. Here you should have something enumerated. You have something, and then just mention that if there is some traceless symmetric traceless case primary. So we have a same conclusion: mu1, mu L of 0, or mu1 over mu L of x, and two-point function. If you consider this one, you have the same two delta, and then C12 is symmetric. So we have I mu1 of x, so I mu L, and mu1 and mu L of x, and it's symmetrized, everything symmetrized minus trace. So all the indices are symmetrized here, all the indices are symmetrized here, and then of course you need to take a trace of these. Okay. So those things, and I call it this one is symmetric of I mu1, so I mu L, and then mu L. I call it this one. That's what's going to happen. Okay, let's stop here. And then this is a way of deriving by using using symmetry. But the next time I will use this embedding space formalism that will just immediately derive this result. And then geometrically it's very clear. And then it's super easy. Let's stop here and then see you next week. Oh, by the way, so you will organize something next week? Tuesday? There is some Tuesday. I don't remember. Tuesday at the cafe, 3:30. There's something going on, and I'll be there. If you're interested, you can come. I don't know the contact. You can ask him. What's the contact? Yeah.